Hi everyone, in today's lesson we're going to talk about right and left-hand derivatives. If a function is continuous at x equals a, it doesn't necessarily imply that it's differentiable. So where derivatives fail to exist? So at a corner or a sharp point. So if you look right here, obviously this function is continuous, but at this value right here, at that corner or that sharp point, it's actually not differentiable. So right here is where it fails to exist. And at something called a cusp, see how this curves in and then curves out? That's what's called a cusp. So at this value right here, it's not differentiable, although the function is continuous. You don't have to pick up your pencil to follow through. Same concept here. This is definitely continuous, but right here, there's what we call a vertical tangent line. This line is vertically tangent. So that is a point where it is not differentiable. And the last part where it would not be differentiable is where it's at a discontinuity. So here is where there's a vertical tangent line, well not tangent, but a vertical asymptote, and here where the function is not continuous, okay? At discontinuity here at a hole. So why is this so? And here's the definition. A function is differentiable at a point x equals a if and only if the left and right hand derivatives are equal to each other. Now remember, this is the derivative formula. It's actually the difference quotient, the f of x plus h minus f of x all over h. So if the derivative from the right is equal to the derivative of the left, then we can say the function is differentiable. And the last thing I want to talk about is continuity. If a function is differentiable at x equals a, then the function must be continuous. So differentiability implies continuity, but the other way around is not necessarily true. So let's see how this would work in an example. Okay, so let's look at the example. It says, use the right and left-hand derivatives to prove that the function is not differentiable, and then graph your result and name the type of failure. So I'm actually going to graph it first, and I'm only going to graph the line 2x plus 1 when x is less than 0. So you could either graph that by hand, or you can plug it into the calculator. So y equals 2x plus 1, and I want all the x values that are less than 0. So 0, -1, -2, -3, -4, and so on. And then the same thing we're going to do for y equals x squared plus 1. And now we want the values that are greater than 0. So 0, 1, 2, 3, and 4. And notice how I put 0 in both of them. Just when x is greater than 0 for the parabola, we're actually going to use an open circle here. And we're going to use a closed circle here. All right? So take a minute, pause the video, and graph these two functions, or one singular piecewise function, and then hit resume when you're ready. Okay, so this is what your picture should look like, and let's just take a look and see what type of failure that I have. And it actually looks like the failure exists right here at this point, and it actually looks like it's turning into a cusp, right? It's curve on one side and then straight on the other. So I'm actually going to write that this type of failure is a cusp. And is the function continuous? And the answer is yes. The function definitely is continuous. You do not have to pick up your pencil to trace over this thing, right? It's definitely continuous, but it is not differentiable because there's a cusp. And let's prove it. And we can prove it by taking the limit or the derivative, right, from both sides to see if the left-hand side derivative is equal to the right-hand side derivative. So let's start by writing the limit, which is a derivative, right? The limit as x approaches 0 from the left. So we're going to use f of x plus h minus f of x all over h. Oh, excuse me, as h approaches 0, right? Now, if we're taking the limit as h approaches 0 from the left, we need to use this left function, right? This is coming from the left. So the left function is actually the line, the 2x plus 1. So we're going to plug in f of x plus h. So that would be 2x plus h plus 1, then minus f of x, which is in fact the line, the 2x plus 1, all over h. And we want to take the limit as h approaches 0 from the left. So let's simplify this a bit by distributing the 2 and distributing this -1. So we've got 2x plus 2h plus 1 minus 2x minus 1 all over h. And again, we're going to take the limit as h approaches 0. So let's see what happens. 2x and 2x cancel. 1 and -1 cancel. So we have the limit as h approaches 0. Now these h's cancel, so of just 2. So this is actually a constant function, so the limit as h approaches 0 of this constant function is actually just 2. So the limit from the left is 2. So we could say f prime of 0, right, is 2, and this is from the left-hand side. So that's the derivative of the function from the left. Okay? And now let's check out the formula from the right. Now from the right, we know we're going to use this curve. So same concept, except now we're going to use the x squared plus 1. So use a different color here. And we'll say the limit as h approaches 0 from the right, and I'm going to write the formula again, f of x plus h minus f of x all over h. So x plus h squared plus 1 minus x squared plus 1 all over h. And we're going to take the limit as h approaches 0 from the right. Okay, and again, it should be useful to you if you've memorized what x plus h squared is. So that would be x squared plus 2xh plus h squared, then plus 1, then minus x squared minus 1 all over h. And again, we're going to take the limit as h approaches 0 from the right. So the x squareds cancel and the 1's cancel. So I'm left with, again, the limit as h approaches 0 from the right of 2xh plus h squared over h, which simplifies to the limit as h approaches 0 from the right of the h's will cancel, so it'll be 2x plus h. And now we're going to substitute 0 in for h. So if we do that, it's just 2x. So our derivative, f prime of 0, is going to be 2x from the right. Okay? So you can tell, right, and this was when we plugged in 0 for h, right? And we just get 2x. That's the work, and that's where it came from. So you can see clearly that the limit, or excuse me, the derivative from the left is 2, but the derivative from the right is 2x. They're not equal to each other. Therefore, the derivative fails at this cusp value right here. Okay? So if you have any questions, now's the time to jot them down and make sure you ask in class tomorrow. All right, have a good night.